Okay, so welcome to 4Keys College online tutorials. So in this particular series of videos, we're going to be talking about transition metals. So we're going to start here with an introduction. So transition metals are found on the D block, which is the central part of your periodic table shown there. So we should understand the electronic configurations of these D block elements. So firstly, the definition of a transition element: it's a D block element that can form at least one stable ion with a partially filled D subshell. So the key point here is stable ion. It forms at least one stable ion. So you see that many of these can form several ions, but they have to be stable, at least one stable ion with a partially filled D subshell. I had to repeat there because this is a very important and exclusive definition. As you shall see, some elements do not qualify to be transition elements even though they are part of the D block of elements. So the D subshell, remember, it holds a maximum of 10 electrons, and we have two elements that are part of the D block elements but do not qualify to be transition elements, which are scandium and zinc. And remember, when you're filling electrons into the shells and subshells, you have to fill the electrons, starting with single electrons first, and then you start to double them up. So let's look at the electronic configurations of the transition elements that we are going to be talking about here. So we can simplify the electronic configurations by writing the electronic configuration of argon, and then after that we look into the 4s and 3d subshells. So we are concerned with these outer orbitals, outer subshells. So titanium, that's the electronic configuration there, and then your vanadium, you can see the number of electrons increasing by one there. Then you have your chromium. Okay, so for chromium, you see that one of the 4s electrons will jump into the 3d to create that half-filled 3d subshell. So all of your orbitals are half-filled there, and that makes it a stable configuration compared to the configuration it would otherwise form. So this is the best and most stable configuration chromium can form. So pay particular attention to this one when you look at these transition elements. Manganese, you have your iron, and you also have your cobalt. Okay, let's move on. You have your nickel, you have your copper. So copper, again, one of the 4s electrons. So you're supposed to fill first your 4s, which is at a slightly lower energy level compared to 3d to the 3d subshells. And remember, these subshells are very close in terms of energy levels, though your 3d is higher than the 4s in terms of energy level. So you see one of the 4s electrons jumping into the 3d there, and that gives us a fully filled 3d orbital, and that is more stable than the configuration we form when we remove one of those electrons in the 3d and put it into the 4s. So pay particular attention to chromium and copper, where you might need to explain why the configuration is unusual. Okay, so those are the two elements you need to pay particular attention. Scandium and zinc, like I said, these are not transition elements. They do not qualify. Let's look at the stable ions that are formed by scandium. So scandium has this electronic configuration. That's the box notation there. But when it loses its electrons, it's going to lose here all the electrons to form scandium 3+, and that's an empty 3d orbital, which does not suit what we said. It has to be a partially filled 3d subshell, not an empty 3d subshell. For zinc, it forms only one stable ion, zinc 2+, and this zinc 2+ subshell, if you look at this would be the zinc atom. This would be the zinc 2+ ion, and also take note, we are losing the 4s electrons first. So that's not a partially filled 3d orbital, rather it's a fully filled 3d orbital. So that's the disqualification there. So like I said, you are supposed to lose. So let's look at an example here where you lose 3 electrons. So that's a configuration there. So I want you to check what's happening when we lose our electrons. We are losing the S2 electrons first, and then we lose 1 electron in one of the 3D subshells. So that's the remaining configuration, and you should always check whether this matches with your atomic number. So if you subtract 3 electrons in this case, this should make sense when you subtract this from your atomic number. So 26 minus 3 in this case, you're going to form 23. So the remainder number of electrons there should be 23. It's always good to check whether the configurations make sense. So remember, we lose 2s electrons first, 4s electrons in this case, and then we go into the D subshell. Okay, so let's move on. Properties of transition elements. So transition metals have specific properties which include variable oxidation states. They form colored ions in solution, and they are also good catalysts. Okay, so we have variable oxidation states, and they also form colored solutions. So I'm going to highlight some of the common colors that these metals form when they are put into solution. So you're going to see later on that the color that it forms depends here on the oxidation state and also on the type of ligand. So we'll talk about ligands later on. Hang on for that one. So the type of ligand and the oxidation state will affect the color. So those are the general colors for some of the transition elements that you are going to come across. Okay, so that's your vanadium and the chromium oxidation states there. We have our manganese and we have our iron. So these colors, we're going to come back to these colors when we talk about qualitative analysis. Okay, so just for you to have a general picture, our transition elements will form colored solutions when they are put into water. Okay, let's talk about metal complexes. So when you dissolve a transition element into water, it's going to form complex ions. So that's another property of transition metals. So let's look at how you can represent transition metals in solution, or the complex ions that they form. So the transition metal becomes a central ion, which is surrounded by ligands. So ligands are lone pair donors. Okay, so these are lone pair donors. So these would donate electrons into the empty. Remember, we have partially filled 3D orbitals. So the ligands will bond and provide both the electrons into the empty 3D orbitals. So remember, when you're representing it, you write your central transition metal ion, and you show the ligands that are bonding to this ion. You show the ligands, which must be lone pair donors, and you also show the charge, and you put a bracket there, and you show the charge outside. So we're going to look at specific examples later on. So what are ligands? A ligand is an ion atom or molecule that has at least one lone pair of electrons. So they can be monodentate, bidentate, and polydentate. So let's see at what's the meaning of this. So ligands which only have one lone pair of electrons are called monodentate or unidentate. So this can provide only one lone pair of electrons. Examples include, let's look at those examples: our water, our ammonia, and those chloride ions. Ligands which can donate two lone pairs are called bidentate, ethane diet, and our ethane 1.2 diamine. And then we have ligands which can donate several lone pairs, and these are called polydentate. So we have a popular one that's called EDTA. So let's end here for now. I'll continue with this series in the next video.